Hello, everyone. Everyone can hear me? Yeah? Good afternoon. Thank you for your patience. I appreciate you came here for the end of the day's sessions. Your patience is appreciated. My name is Savine.
I'm Michael Reese.
Michael Reese. We both work on the Azure Data Lake team. More importantly, I'd say we both work on, our official group's name is the Big Data Analytics team at Microsoft. So we work on all the big data products. Azure Data Lake Store, effectively, the Azure Data Lake Analytics, HD Insight, and underlying it all, Microsoft's internal data lake, which is, I think, now storing northwards of 5 exabytes of data in a data lake. So a lot of the learnings we have in that data lake, which is called Cosmos, by the way, unrelated to Cosmos DB, are going to show up in data lake. So today's focus is going to be about using existing language skill sets and scale out, really. So we're going to focus a lot on Java and Python. And more importantly, we're going to talk to you about a pattern of doing data in the cloud and how Data Lake fits in, and some of the key points that we've recently updated to make the product better addressing these scenarios, as well as get into the meat of how to use open source formats, languages to do big data processing. So I will start with, so Michael, can you change it to, please, sorry, my mistake. Yeah, there we go. So what you're seeing now is a very simplified diagram of probably the simplest way I can explain the pattern we're talking about. And there's nothing really vastly unique or different from what you've seen probably in previous presentations. We have an ingest phase, we have we store data in the lake, we prep and train and model and serve. And the unique things we're going to call out today are what are at scale. And when I say at scale, I'm talking about not gigabytes, not 1 terabyte or 10 terabytes, but starting at, let's say, 50 terabytes and beyond. What does it look like when people ingest a lot of data? And what are some of the unique issues they hit? And of course, relating to the topic today, how do Java and Python relate to those topics? And then number 2, what actually happens in Data Lake, with Data Lake Analytics? How do you prep and train data? And so we're going to show you how to take a massive amount of data, process it using Java or Python, and then prepare it for use. And the specific case we're going to talk about today is how do you use it in an interactive scenario. There are actually several ways you can use data in the lake interactively. One is, of course, using Polybase from SQL DW. Another one is using, for example, Hive LLAP with HD Insight. And of course, the one you see so much attention paid to today over the last few days in Build, which is Databricks. So Michael is going to demo that. So we have, I think, 5 or 6 kind of amazing demos for you. They're pretty in-depth. And I know there's a 400-level session, so please don't be afraid to ask very detailed questions. Trust me, Michael is the guy who can answer the detailed questions. So let's go over what landing and cooking looks like. But before we do that, we need to do a little bit of a refresher course on the query execution model in Azure Data Lake. And again, this is a batch query execution model. So what happens? You author a useSQL script. It enters the system, right? It's compiled. So a useSQL script is a logical description of how to transform inputs to outputs. It doesn't say anything about how many resources to use. It's purely logical. You assign, when you submit the job, a number of resources called AUs, analytics units. You could call them nodes for right now. Each one is about 2 cores, 6 gigabytes. And what happens is the compiler analyzes this logical description. It analyzes where the data is, and it develops a plan. Or it has actually several names in our system. It's plan, algebra, job graph, and that's the first thing you're seeing. And then the optimizer kicks in. And by the way, the optimizer kicking in not only as the job is sort of before it works, but also as it's going on. But the key thing the optimizer does is it looks across the network in the data center, and it's asking some very fundamental questions. What is the logical description doing? Is it joining? Is it combining? Is it aggregating? Okay, so the operations. Number 2, where is the data? Meaning, where is it in the network? Is it in a certain rack of machines? Is it within a subset of those machines? Is it further away from where the computation is going? It will try to schedule work that is computation on the nodes if possible. If not on the nodes, it'll try to schedule it close to the nodes, right? There's several layers of hierarchy here, and that's what the optimizer is trying to figure out. It's also doing all sorts of standard optimizations like removing code that has no impact, right? not quite dead code, but a code that has no, it's idempotent.
Yeah, for example, it might push a predicate up to reduce the amount of data that flows between stages and so on.
So then once the plan is optimized, and we really work at making sure the plan is optimized. We spend a lot of time on it, because the more time we spend optimizing, the more money people save with the product. That's one of our focuses in Azure Data Lake, is the continual saving of money. So we spend, our compilation times are like maybe 16 to 30 seconds, as opposed to you're used to half a second with C#. Why? Because we're doing a complex analysis to save you money. If you're processing 1 gigabyte, this doesn't help you. If you're processing terabytes, you will start to see the effects of these optimizations. So once the plan is ready, we actually generate code. And this phase is called code gen. Now, interestingly enough, you've probably heard that USQL is very, it's based on C# as a language. It features .NET data types. It'd be very understandable if you thought that USQL was compiled to C#, right? In fact, that's the way USQL used to work internally. About, I think, 5 years ago, we switched it. USQL actually does not compile to C#, even though it uses .NET data types. It actually compiles the C++ code, right? And the C++ code, unmanaged code, is executing in our network. Why is that important? And this was, by the way, a colossal effort. The reason we did that? To save money, because every job in Microsoft got about 10 to 20% faster just by using unmanaged code. So now the code of the job, what the job is doing, is understood. Every piece of the work. And I'll return to this theme of pieces. It's then going to be the job and its work and its understanding of where these pieces of work are then scheduled in the system. That's this next phase. And then it's sort of managed. All these pieces of work are running, and someone determines whether I should retry a piece of work. And a piece of work, by the way, is called a vertex. These vertexes are running on Yarn containers. The containers are not just processes. They're actually fully isolated VMs, right? So the pieces of work are then computing. They're reading and writing data. Most notably, they can read from data, let's say Data Lake Store or Blob Store, but all the intermediate, temporary data never travels across the network. It's actually stored locally on those compute nodes. That actually means that jobs are not only much faster, you're saving I/O costs, right? Then finally, the nodes, these pieces of work, the vertices, write their outputs back to Data Lake Store or Blob Store. This phase is called finalization. And then, of course, those files, those data sets can now be used. Okay, and I'll skip over the animation there. And I want to give you we'll be showing a demo of this via Michael's demo in a minute, but I did want to give you a sense of what this actually looks like. Can you raise your hand if you've used Data Lake tools for Visual Studio already? Okay, so you have a background. How many of you know about this view called Vertex Execution View? Okay, only 2 or 3 of you, okay? This is a very powerful view. I wouldn't suggest jumping into it every moment you want to find out about a job, but for the purpose of this discussion, you should examine these things. Yep. So when you click on Vertex Execution View, you'll see all the vertices of the job, all the pieces of work. And Michael, the number of vertices can vary from 1 to, what have you seen?
Well, I've seen jobs with 100,000. 100,000
vertices. That's an extreme case, but that's how much the thing can scale. And for each vertex, it is important for Michael's demo you understand what these colors mean. So first of all, there are 2 vertices. Actually, there are 4 in this picture. And they all go through this life cycle of blue, orange, and green, which means creating, queued, and running. Now, just first thing to notice, a vertex, no matter what you're doing, has a startup time. And I believe on average, and Michael, please correct me, a vertex takes about 3 to 5 seconds to start up in general. That's about right.
It depends also how much user code you're deploying. Like the more user code, the more assemblies you are referencing, or the more resources you deploy, the longer it takes, because that all has to be
That's
copied.
Part of the creation process, actually. And so look at the yellow time it's called queuing here. This is not related to job queuing. This basically means the vertex has been created, meaning all its files have been assembled on a container, but it's just now waiting for that container, that AU, to stop doing what it's already doing and then start on this vertex, this piece of work. So you see, this one's waiting. There's nothing wrong with waiting, by the way. There are maybe many other vertexes scheduled on this container, and so it's just waiting for it to start. Notice the green. The green means the actual work, when the vertex started and stopped. Notice the green, I'm going to guesstimate here, it took about like a second or less. right? So notice you're paying, it's interesting, this work, there's a very small amount of work relative to the vertex creation time. This is actually key to some of the performance problems that you might see in USQL. And we're going to show you how we've addressed some of them, both in terms of just working on large amounts of data sets and specifically for Python. Okay, so again, this is very important to understand if you're a USQL developer, as well as for understanding Michael's demos. Okay, so I can never give you exact numbers about internal data lake. I told you it's north of 5 exabytes. I can tell you it's also north of 5 billion files. Okay, so I actually analyzed all of those files, and I did a distribution of a histogram of the file size. So surprise, surprise, big data is actually, at least in our experience over the last 8 years, and this has been a very consistent curve, is really made of very small files. I would say 85% of the files in our many exabyte data lake, 85% of them are smaller than a terabyte, right? Or 95% of them are smaller than a terabyte. 85% are smaller than a gigabyte. There's lots of small files. There's lots of reasons this occurs, but we do get outliers. You will see files inside of Microsoft, which I think it used to be the biggest one was about 800 terabytes. Very recently, we found one that's 1.2 petabytes, a single file. But those are rare. The most common thing is that people get small files, and the reason for getting small files is people are ingesting small amounts of data, for example, from devices, right? So this poses a very special problem for USQL to deal with lots of small things. Now, Michael, why don't you start with the how we deal with the files in general.
Sure.
We'll build up.
So how many of you actually have used USQL so far? How many of you have heard of it? Have seen it, maybe? So as we mentioned at the beginning, it's a 400-level session, so I apologize for anybody who was coming hoping to kind of learn from the beginning. But one of the things that you will see is I will show you code, and then we can talk a little bit about what the code is doing. And so feel free to interrupt and ask questions if you have any questions in terms of understanding. So one of the capabilities that we have in USQL is because it is analytics language that operates on data inside a data lake, it gives you not only the ability to query tables and views as you would in a traditional database environment, but it also gives you the ability to operate on any arbitrary files inside your lake. And now, of course, files are normally not schematized, so you have to schematize them on read, and the operation to do that is an extract statement. And the extract statement, basically, what you can see here is it basically gives you a schema as part of the extract clause. Looks like a relational schema. It has key value pairs of column name, column type. The type is C#, which is kind of like one of the differentiations between USQL and other SQL dialects. And then you go and read from a file. Now, you can also read from an enumeration of files, like in this explicit list that you see there, where I basically enumerate all the files explicitly, or I can use what we call a file set. A file set is nothing else than a pattern inside my path, and I can lift parts of the patterns, if I so choose, into the column and make them part of my row set. So I basically lift file metadata into my row set data layer. So it's kind of like an interesting way of doing that. And so in this case, for example, the example you see here is basically I have two columns inside my input files, user and ID, and the suffix is being taken from the path. And then I use basically my extractor. In this case, we have some built-in extractors. We'll talk more about data formats a little bit later. And now I can have more complex patterns. So for example, I can, like in this case, have a date-time pattern that I can specify, and I can specify more than one column if I want to. And more than that, I can put predicates on so that I only go and read the files that fit that predicate. So in this case that you see here is I'm only actually reading the files that are in the directories that fit between January 1st, 2016 and probably February 1st, 2016, assuming that this is the right format.
It may be worth re-emphasizing, because I know not all of you use SQL, that it will, for a lot of people, honestly, it will look like the right side is saying, do this first, then do this second. But that's not actually what's going on at all. Both those expressions are being compiled in one big query. So when Michael talks about predicate pushdown, it's not reading 100 files and then filtering out 2 or 3 of them. It's actually pushing down this predicate of where the where is into the extract. So it's avoiding reading all those files.
Yes.
That's very critical to understand. It's not obvious the way the code is written, but it requires that you know that this is all one big expression, actually, when the compiler thinks of it. It
Correct.
isn't imperatively doing one thing then the next.
So, yeah.
So does that mean that I can actually have multiple queries split up in my NoSQL, and that improves my readability of the query?
Yes. So for example, most, I would say a lot of T-SQL queries tend to have a lot of what correlated subqueries. They go to the right a lot. They're thick. In NewSQL and in Microsoft, we know, when you look at jobs, they go to the right only because the number of columns is big. They grow downwards a lot. Everyone sort of, let me filter out this condition, let me filter out this condition, and let me filter out this condition.
Or add me this join and get some reference data in and so on. So yeah, it's a very good question. And one of the design principles was that we try to give you a single script is a single query, but you can write this the query more in a script-like fashion where you have multiple statements that reference each other. So the variables that you see here are names for the expressions and not actual containers containing data at the logical level.
And Michael, what's the closest equivalent in T-SQL to this row set?
So the closest equivalent in T-SQL is common table expressions. So CTEs, except for that, how many of you write CTEs? More. There's 5 years ago or 6 years ago, it was like 10% in the room knew what a CTE was. So, but it is easier even than CTEs because it kind of follows the standard statement paradigm. And so it's easier for people, I think, to understand than having to remember how CTEs nest and so on. So anyway, one of the things that when we released this file set feature, we were bound by some of the scalability restrictions we had in our internal system on which we based ADLA. In our internal system, we basically have a captive audience. We can tell them, build big files. If you don't build big files, it's your fault.
Yeah.
And if you come back, we tell you it's your fault, and you go back and build big files.
No.
If I go and tell that a customer here, they will probably walk away because they will feel abused by us. So we did have a limit on those file sets back in our internal system of about 3,000 files, and then the compiler would just time out. Now we just had
No, the timeout wasn't accidental. It was a deliberate timeout.
Yeah, so we have a limit during compilation of about 25 minutes.
Yeah. And can I just add one thing?
Yeah.
So what's happening is that the compiler, it has to know all the files. One of the rules of USQL is all the inputs must be understood. And so what it would do is linearly go down the list. And it would, no kidding, it would just verify the file existed, okay? It doesn't seem like a very expensive operation, but over a network, it was 248 milliseconds, okay? Which is really, when you get into the thousands range, starts to add up to real time.
Yeah. And then that, together with the not so efficient way that the CodeGen was creating the code, added up to, after about 3,000 files, we basically hit the 25 minutes.
Yeah. So now the lookups are multi-threaded, and the code generation part is much faster. Right?
So now we can basically go up to about 100,000. And this has been in production release since about a month or so. And the cool thing is you actually don't need any syntax change to make use of that. We actually had one customer running a job just before we upgraded and the job right after we upgraded, and he complained that the old job was much slower than the new job because he thought there was a difference somewhere. And we looked at it and said, no, you are just getting the performance improvements that we just released.
Just of finding out the files, not even running the code.
So,
I think we've had a customer ask for, I actually didn't believe this when I first heard it. Yeah. They didn't want 100,000 files. They wanted
2 million.
2 million files.
Yes.
Yeah, there we go.
So we are not at 2 million yet, sorry. Maybe we'll get there. So now one of the other problems, of course, is if you have small files, even if we are better at the compilation of the script and create you a better plan, we currently, per default, give you, in most cases, one vertex, meaning one of those units that you have seen of work that Savin talked about, per file, which means we spin up a VM for every file. So imagine you have files that are in the bytes to maybe low megabyte range. You're spinning up a VM just to do a few milliseconds of actual execution work. Not a very good utilization of your money and the resources. So we have added currently in preview a feature called input file grouping, and I will show you that in a minute actually, where the job manager and the optimizer collaborate to figure out how many files it should pack into Vertex. So it will try to pack up to 200 files and up to about a gigabyte of data, whatever comes first, into Vertex. It actually sometimes packs less because there's other stuff that obviously goes into Vertex, so it kind of tries to balance that. And at that point in time, you actually now have a much better resource utilization. So let me show you that in an example. I actually have two examples here. The first example is a script. Let me increase the font size here. What this does is, it does some image extraction. So you see here a file set that goes over a set of images. Name, format are the two virtual columns. It uses the Cognition Vision image tags extractor, which is an extractor that we provide as in an extension library, which uses the Cognitive Services APIs, Cognitive Services code actually underneath the covers. And then I restrict this to about to only JPEG files. So there are about 100 files in that directory, and I run this job now against only the JPEG files, which are I think 28, and then I do some further processing just to like output it into result. So I did run the job already twice. The first time I ran it without the new input file grouping. Oops, my zoom it just must have crashed. My apologies here. Okay, that should start it. Okay, that's better. So if you look at this, 26 files as input. These are all JPEG files. It runs on 26 vertices. Each vertex takes about 8 seconds, and then the rest is kind of just collecting. If you now look at this vertex execution view that Savin showed earlier, I can actually do it. Oops, that's not what I wanted. I can do it down here too. Make that a little bit bigger.
And each blue segment's about 5 seconds roughly,
yes.
right? Yeah.
It's actually, yeah, it's 8 seconds,
8 seconds.
here because it deploys some additional code.
So notice the ratio of blue to green.
Yeah. So now I basically spend 8 seconds to start up and then a few seconds to until my scheduler gets everything through. And then I spend like 1 second's execution. Not a very useful use of the container. In addition, obviously I use many of those. I use 26. So if I do the other one, now I run the code with that input file set grouping on. And now you notice that I'm only using 2 vertices. So I'm already cheaper in terms of numbers of resources that I'm using. And if I go into the vertex execution view, now it's not only less vertices, but it's actually doing more work here. Now, there is a potential drawback in terms of doing more work at less scale, which is that as over the duration of your job, you might actually do more work later, and you will have less degrees of parallelism, and so you might actually spend more time. And I have one example here to show you that. And that's a similar job here. what this does is it basically uses some book extractor that I wrote that reads some text documents, Gutenberg project library book documents, and tries to extract authors' titles and book parts in some way. And then to each one of those parts, I then apply the key phrase extractor. That is, again, something that is part of the cognitive extension pack. And then I basically output that down into a file. So if I look at the first execution here, I executed this, again, without the input file set grouping. I get 28 documents and 28 vertices. And then down here for the processing, so the extraction is my extractor that basically chunks up the books and gets some properties out. And this one down here, that's basically the actual key phrase extraction. So it operates in parallel, 28 parallel with 25
that's great,
seconds.
Right?
So that's awesome. Yeah. High degree of parallelism. The job can be done in about 3 minutes. We have a AU analysis tool here that we will see later. One thing I want to point out here is that it calculates, among other things, how many AU hours it was using. In this case, it's 0.7 AU hours. So that kind of translates then into cost, what you pay for the job. Now, if I look at having it submitted in, again, with the input file set grouping, again, it gives me about 2 vertices. I think the 2 vertices is just the smallest thing that it does. And then down here, of course, the process is also 2 vertices because it tries to not repartition the data because now we can just submit the vertex that does the process onto the machine that just did the extract to kind of keep data locality and not have to move data around. Mm-hmm. And so what that gives me now is, however, that because there is no big distribution, it gives me an average execution time of 4 minutes. And actually, it's unbalanced.
Even though, by definition, these books are perfectly parallelizable in the processing.
Yes.
Right.
And if I look at the vertex execution view here, down here, I actually see that one of the vertices produces almost 2.5 times as much as the other vertex. So there is an unbalance here. So I'm basically not getting necessarily parallelism. However, the interesting part here is, again, you do more work, and if I go back here into the AU modeler.
Oh, that's quite interesting. The cognitive thing, the green, is very long. I mean, that's where the real bulk of the work was.
But I'm still, even though I'm running longer, it's a cheaper job because I'm only using 0.2 AU hours instead of 0.7 AU hours. So it's still about 3 times cheaper.
It's cheaper, but is it as fast?
No, it's slower.
It's by how much?
It's about 3 times slower.
3 times slower.
So there's a trade-off here. So once we release that feature, we will give you the option of turning it off if you are in a situation where this might be the case.
Michael, I know we get this question all the time. The previous stage is a small number of vertices. And everyone intuitively knows that their data is perfectly parallelizable. Yep. Can someone force a repartition?
Yes. So there are some data hints that you can apply on a row set. If you over or under specify the number of rows that expression returns, then the optimizer will use that number instead of its estimates.
So that's another option
here. And then
it
might be over partitioning, so that's another option. A third option is that you actually give an explicit partition hint. But the partition hint only helps you if, because that's a plan hint, if the query optimizer actually considered the plan that might that this hint kind of then selects. So normally we recommend to use the data hints for that.
Right. And I think it's a great point Michael's talking about. The general philosophy for uSQL is if you can tell us more about your data instead of telling us what to do, life will be better for you.
Yes.
So the data hint is telling us the nature of the data partitioning. The telling us what to do is like, we could override it. It may not help us, actually.
Exactly. Yeah. So here you basically just have a summary. Yes, question?
Regarding the data hint.
Yeah.
Can I use relative terms? Because right now data hint give me amount of records, 1 million. But what if in one case my one data set is 1 million and another is 100?
So just to repeat, just to repeat the question, Today, when I give a row count hint, I have to give an absolute number. And the question is, can we have a relative number, like relative to maybe the estimate that the optimizer currently does or something? This is on our long-term plan, but it's not yet committed. There is a link, though, that I would recommend you guys to go and actually execute, aka.ms/ADL feedback. That takes you to our user voice page. Vote frequently and often. It will bubble up, and at that point in time, it will actually get more weight in like planning and so on. Yeah. But I've been thinking along the same way as well, that we need some more of that. So now let's go and look at some other extractors. You already saw like the built-in extractors, CSV, TSV, or text for arbitrary delimiters. We have several major options there. One that we recently added is Windows 1250X encoding support. So if you have like ANSI code page files, you now can extract those without having to convert them first into UTF-8 or so. Default still is UTF-8. We do have for extractors skip first and rows. For outputters, we have output headers so that you can create a header line if you want to based on the column name that your row set has. Quoting has the ability to handle quotes or not. One of the important aspects, though, there is that it does not guard your end-of-line character. So the end-of-line character, because of the way that we parallelize the processing of the extraction phase, we do not know if an end-of-line character is within quotes or not at any point in time, except for the first extent. So what we basically do is we always break the line at the end-of-line character, even if it's within.
Even if the end of if curl-if is found within a quote,
yes, even
it
if
will still break.
It will still break.
Got it.
We are thinking of potentially adding an option which then takes the parallelization away and gives you that capability. Right now, you would have to write a custom extractor to do so. You can also go and escape your characters, actually. So there's a last option there which gives you the escape character option. But that means that your input data needs to be prepared for that. So if you have an Excel CSV file, obviously that will have carriage return line feeds in it. Silent true or false, I'm not going to go into a lot of detail. One thing I want to point out on this is that it has performance implications. I see a lot of people use silent equal true because they have a little bit bad data. It will run slower than if you are actually trying to make sure that you have the right data. Now, I already talked about it will execute in parallel. Basically, if you have a file set, obviously, as you have seen, it will use the file set ability to scale out. Otherwise, it will take, for every file that is bigger than a gigabyte, it will take a gigabyte per vertex. And so if you have, let's say, extract, we will see 3 gigabytes or so, you will get 3 extract vertices. Every vertex will then execute 4 extractors in parallel inside, so you will get another like 250 megabytes per extractor. And that's what the extractor sees, plus a 4 megabyte overscan, so that we find the end of row if the row is not aligned with that block of data that we are processing.
So what's sort of the normal row line size people should work
So
with?
the maximum input record size and the maximum row size right now are both 4 megabytes.
4 megabytes, okay.
Yeah.
But 4 megabytes UTF encoded.
No, that's whatever is on disk.
Got it.
And then once we have string data types, it's 128 kilobytes per string right now, and we're working on increasing that to give you a little bit better larger strings. So as a consequence, as I mentioned, large files, specifically CSV files here, will get parallelized. And an extractor instance will only see its data and nothing else. So don't assume like that you have a global view of the file when you're operating in a parallel extractor. The extractors support column pruning. So that means if I do not, let's say, right now, especially CSVs, because I don't know what the schema of a CSV file is, I have to give the schema in the extract clause. And I have to give it fully because CSV is positional based. So I have to say first, second, third, etc. Don't worry about having to write them all out. We have a tool that helps you generate it. If you only use 2 of those columns, the optimizer will push those columns into the extractor and will only extract those 2 columns. It will not try to extract everything. So here's the next one. So we do have Parquet support now. It is currently in preview, but it has been used quite a bit already by people inside and outside. We do have no options on the extractor. Everything is read out of the metadata of the Parquet file. We currently have to give still the extract schema though, although we are going to release extract star soon. That will basically pick up the schema out of the Parquet file because the Parquet file actually has a schema definition inside. And then basically we give you the options of, on the outputter, to specify your row group size either in terms of bytes or rows. And we give you the ability to encode the columns with different options. Now, the important ones here are the precision and scale. The datetime precision, which can be micro, milli, or days. I noticed that some Spark engines can't cope with micro, so you will have to use milli for that. And compression is uncompressed, obviously default. Snappy, Broadly, and gzip are the supported compressions that we have. Which again, be careful if you, for example, use some Spark engine, make sure that you have the codec for the compression that the data is compressed in, otherwise it will get error messages.
What's the one that everyone supports?
Snappy is kind of the Snappy and gzip, I think,
okay.
are the
Broadly is very new, as I recall.
Pardon?
Broadly is very new.
Yeah, Broadly is a new one,
okay.
And at least I know when I tried HD Insight Spark's notebook, it complained about Broadly, so I had to change it to Snappy. I like Broadly because it sounds like bread.
I knew it.
Yeah.
I knew it.
So again, in the Parquet, the current Parquet extractor only executes in parallel if you use file set definitions. We are working on a version that will parallelize a little bit more when we have more metadata information about what the row groups actually contain. But without having some semantic information about what the row groups actually are partitioned or so, it's very difficult to scale that out, because otherwise you just have to do a lot of data movements again, and then you're kind of losing the benefit of scale up. So as a consequence, we recommend that you use about 300 megabyte to 3 gigabyte in size Parquet files, not much smaller because then you're over partitioned, not bigger because then you're under partitioned. We do, again, already support column pruning. So if you are requesting a column that we will only extract the columns that you actually use inside your script, not just the one that you have in the extract statement. A pro tip is to help you with that aim is to use the file set output syntax that we currently support, which gives you one file per vertex. And with the currently in private preview output partition, output file set feature, you can then do that based on that. It will not give you size-based partitioning. It will give you, obviously, logical partitioning. And furthermore, I already mentioned, so we are in public preview for Parquet. We are looking at adding usequel tables that can use Parquet as a storage format, as an alternative to the current structure stream format. And we are expecting everything to go into GA in the second half of this year. The extractors might be earlier, and the tables might be a little bit later. Other formats that we are working on, we do have a private preview for ORC. And the same as in Parquet, we are working on actually having a table preview as well, and GA in the second half. In terms of JSON, XML, and Avro, which is kind of the next set of formats that people would like us to provide, we do have longer-term plans on providing built-in support there. There's currently no ETA, though. Originally, we were planning on having JSON available in the second half of this year, but there has been some reprioritization of some work happening. So you're basically best served with taking a look at our custom UDO library on GitHub, see if that works, and if not, it should give you an idea of how to write custom extractors and then use the reader interfaces that Newtonsoft, for example, offers, or the system.xml APIs offer to kind of get higher performance and less memory usage, etc. Also, we have obviously the cognitive services extractors that you've seen earlier. They are there both as extractors and as processors normally. The reason why we have both in both form is if I already have the data inside a table, for example, then I don't want to write it out into a file and extract it. At that point in time, I need a processor. And an extractor allows me to operate on a file that is bigger than the row size, as long as the row size I'm producing is less than 4 megabytes. So if I have an image file that is 5 megabytes, for example, I can operate on that with the extractor. I couldn't operate on that with a normal extract into a byte array column because that would be bigger than the row size. We also have other custom formats. Several people in the community have stepped up to give additional interesting extractors. I've written a few. Two that I want to kind of call out that we really didn't have a lot to do with, but they have been provided and people are using them, is a PDF extractor.
Sorry.
This on that. So he's allergic to PDF, apparently. PDF extractors and Excel extractors. And so if you have Excel documents and you need to like find in which sheet or which cells and so on, you want to kind of extract those, that's kind of useful as well. So there's a whole ecosystem that you can build extractors or find extractors for. So now let me show you how to generate Parquet. Let me go back to my demos here. So here is a simple script. Obviously, the way that we enable preview features is we have this system setting called features preview, and then you can like enable different preview features as they are there. These flags don't go away. So if we ever release it, the flag is still there. It will not do anything anymore. But sometimes you can still use the flag to turn the feature off, like for example with the with some of the file set optimizations. So what do I do here? I'm reading a line item table that is about 3 gigabytes in size, and an orders table that is about 180 megabytes. And so I just schema
those tables are just text. Right?
These are just CSV pipe delimited files here. So I'm using a pipe delimiter extractor here to extract this information. Very simple. And then I write them out using my Parquet outputter. Now you will notice that the outputter here is using snappy on all the columns. The syntax we are actually working on, that parameter there might be better parameterization eventually coming, like type-based or name-based.
Do they have to name each column the compression type? Or can they just assume to be something?
We do have, you have to give, for each column that you want to have compression, you have to give that.
Yeah.
We are looking at making it a little bit less verbose.
But if I say nothing,
then
you just won't
compress.
Got it. You don't have to.
Yes.
Okay, got it.
And because I'm using Parquet here later with Spark, I'm telling it to use milliseconds resolution for my datetime and not microsecond, which is the default. And so I basically run this job. Now, let me see. I should have this job already here somewhere. No, that's the wrong one. Let me just go back here quickly and open this. You can see how all the nice tooling works here. Here is the last script that I executed. So you see here, what it basically did was the line item table was reading in 3 vertices, read about 2.4 gigabytes, 18 million rows, plus or minus. And it did about 1.5 million rows. And it generated a single Parquet file each. And the Parquet file was, in this case, about half a gig in size because of all the compression, and about 56 megabytes because of all the compression compared to the original pipe-separated text file. So we will use those files later, so keep them a little bit in mind. But that's kind of easy. What I also do is I can then use these Parquet files to join, obviously. So here, I'm doing my extraction. using extractors.parquet. As I said, right now I have to give the whole schema. Eventually I can just say extract star, and so you don't have to repeat the schema. And then I just use them as normal row sets and do my joins here, etc.
There's no difference between these row sets from Parquet at this point.
At that point in time, they're just row sets. Yes, the Parquet reading, of course, was more efficient. We did the column pruning, like we only pushed those columns out that we need. And of course, because it was compressed, there's less I/O, so it's probably going to be cheaper, both in CPU and I/O cost.
I noticed we didn't. Can we still use predicate pushdown when we extract on Parquet files? It's still possible.
So predicate pushdown right now is not possible. It's like CSV right now.
Yeah.
We do not know where the data all lives. Like the row groups, they have some statistics that tell you what the high and low watermark is in the row groups. But unfortunately, there is no guarantee that these row groups are actually partitioned in any way, shape, or form. So unlike tables, and that's why tables make sense, tables will give you an additional level of metadata that then will give you a guarantee that it's partitioned. So if you want to just use files and partition, and that's a good segue, you're actually doing what people would be doing when they do Hive or a Hive metastore or so. You actually output the files into a partitioned experience, and we'll see that later.
Yeah.
And just kind of, let's see the join here. Quickly go to the job browser here. If I look at the Parquet join here, that took about 1.3 minutes in terms of runtime. If I look at the same join, doing it using my text, and of course I used like 2 AUs in parallel only. If I look at my text join, that was on this data volume about the same, but if I wanted to be the same speed, I would have to use 2 times as many resources. So I would have to use 4 AUs because I'm reading more data. So you can imagine if you scale that up into the terabyte range, at that point in time, it suddenly becomes a much bigger difference, and Parquet actually gives you a lot of savings in that context then. OK, so let's go now back to the presentation and switch from our flexible formats to our flexible languages. So one of the themes, and I hope people that left didn't want to hear this and then got discouraged, we also want to talk about languages. So far, we have seen all our code use basically .NET libraries. Now, I'm a .NET guy. Many of you are, but not everybody out there is a .NET guy. There are people out there that do Java and R and Python, etc. So basically, USQL is now a framework that allows you to scale out all the languages that you write code in. Now, I'm saying allows you to do now because our internal version can. This is all stuff that I'm showing you right now that is going to go into preview within the next 2 to 3 months in terms of availability on the cluster. So you basically take your .NET code, your Python, your Java code, and the R code, and you use the USQL framework to scale it out in the way that we talked about earlier. And so basically, USQL now is the framework that allows you to scale out your custom imperative code in a declarative SQL-based framework. So the way that this user code gets written is often as what we call user-defined operators. So an extractor is a user-defined operator, for example, that takes files and turns them into row sets. We also have outputters that we just talked about that convert row sets into files. And then there are a bunch of relational operators that take an arbitrary number of rows or a very specific number of rows, like 1, and produces another 1 to many rows. And the reason why they are called differently is because they are appearing in different syntactic contexts, and they have different cardinality semantics, so it gives the optimizer a better understanding of what actually happens. So for example, a processor is just a very special case of an applier that gives me a single row. But knowing that you have the exact same cardinality as your input is important for the optimizer to make good estimations. We do have combiners, which are kind of like user-based joins, and reducers, which take a partitioned row set, so a bunch of rows that are partitioned according to some partition criteria, and then allows you to do reduction or explosion of them.
So roughly speaking, they're like super aggregates.
They're
right?
super aggregates. It's like reducers, basically, in the standard map reduce idea as well. Now, they are called, as you have seen, with these special expressions, extract, output, etc. So let's take a look at an example here. On the left-hand side, from your point of view, you see like a uSQL script that does a lot of like extract, select, and process output. And then on the right-hand side, you see the job graph. Now, each one of these statements, extract, for example, they invoke some user code, which is basically the extractor or the user-defined function in this case as well that has been specified. Now, if I do a processor, that's the same thing. There's a process node, and that might contain user code. And then the outputter, again, the same. It might contain user code. Now, the interesting part is in our earlier versions, you wouldn't be able to tell unless you dig into the vertex to see the operator graph, whether it has user code or not. Now we are basically giving you an annotation on the visual clue to tell you that, yeah, there is actually .NET code in here, or there's Java code in here, or Python code, etc. Now, many of the compiled languages, at least, they need, we give you the option of registering the code inside the uSQL metadata service so that you can share it with other people so they don't have to like remember where the files are or have to like create their own files and deploy them all the time. And now we call them uSQL assemblies. I know Java doesn't have assemblies. They have jar files. But the assembly here refers to the uSQL metadata concept and not the code concept. So right now it's not there, but eventually we'll have Python assemblies, which is just the text file. But it's a uSQL Python assembly. It's not, it's just a unit.
So
to
a
like
uSQL assembly means just like a package, really.
It's a package of code objects that you can refer to all at once.
Does not mean, oh, it must be .NET assembly.
Exactly.
Could be any of these.
It could be anything. So you'll reference them. You have some ways of referencing system assemblies. You have ways of enumerating them. We also have catalog views by now, so you can use catalog views as well. And you can obviously drop assemblies. By the way, we will have the slide deck on the share. Blame Savine for not uploading it earlier. And then we have another way of deploying resources onto these vertices so that you can make use of it. That's using a deploy resource statement. That's right now the way that we deploy Python code, for example, and then invoke the Python code.
Its original usage was more like someone needed some reference data on each vertex. It's like a text file, so they deploy that to each vertex.
Config files.
Config files. Yeah. So we've actually expanded it to be like extra code you need.
Yes.
Right?
So we'll see some examples of that when we go into our examples here. So first, let me show you Python code. And I have to here give a shout out to my engineering team that has worked hard the last 2 weeks to make these demos possible. It's not just like making the code available, but actually deploying them in a way that I can use it and demo it here. So let's switch over and take a look at the Python example. So here is a Python library. This is currently using a very special runtime. So if you can remember that GUID or so, then you're happy. And then you can use enable Python UDO.
I don't think that's deployed to all.
It's only deployed to one of the, the areas.
Don't try to use it quite yet.
Yeah. So in this case, I basically want to show you a script that uses a Python extractor, a Python reducer, and a Python outputter. Yeah.
So one reason, you know, I'm a Python guy since Python 1.0 in 1994. Yeah. And so, for example, they're often like the bread and butter of the Python world used to be text processing. Now I think it's machine learning. But there are libraries like Beautiful Soup. Anyone, if you guys know that, that's for like really fun parsing and tearing apart HTML. HTML, yeah. And so doing that in Python and Beautiful Soup is much easier than in like in C#. Yeah. So this is sort of that use case. It's so common to see Python used for messing around with these text
Yes.
files, right?
And of course, that's like a perfect example for writing an extractor over HTML files using Beautiful Soup.
Beautiful soup.
Yeah. Now, I wonder if that is part of the lake or not. Yeah. Anyway. So what I'm doing here is I will show you the Python code in a bit. What you basically write is you write an extractor or outputter in .NET, you're now or C#, you're writing one now in Python. So there are some APIs that we provide that you kind of and some patterns that you follow. And then when you want to invoke it, you can also inline, for example, your Python. So in this case, I also inline just the outputter here. And if you see the inline, it's a class. It has an initialization that would allow you to, for example, parameterize it or do some other stuff with it. Then you have the actual outputter. So this is basically the kind of pattern that you have. You implement the output method that has a self, the row that it gets, and the output byte stream. So you basically get the stream here. You get the schema row. You check a little bit if the schema is below the row size here. And otherwise, you basically iterate over every one of the indices here. And you basically take the first column in the row set and write it out. If it is, if it's a string here, you basically UTF-8 encode it, so you have UTF-8 encoded files here per default. Obviously, you could add this up here as a parameter and allow people to specify what encoding they want to use. And you add a pipe delimiter here. Again, that's something you could do as a parameter if you so chose. Now, an interesting thing that the Python outputters have, but the .NET outputters don't yet, is the ability to finish off a file. So in this case, the finish actually goes and writes an end of row set string at the end, so you can add footers to your files.
So you mean of n arbitrary vertices, the finish method will only be called on one of the vertices?
The one of the vertices that writes the last range of the data.
That's very convenient for Python. Yes. I hope to see that in C#.
Yes, me too. And then, of course, a way of writing headers, too. So here you basically have the extraction. Now, the way that you invoke the Python thing is we have an extractor.python. And you provide two arguments. The first one is the prologue argument. The prologue argument is nothing else than setting the environment up of your Python, like the import statements, like the default definition of your code that you want to do. So in this case here, for the extractor, it just tells me to import the Python extractor, which is part of the Python extractor.py file that you deployed earlier. Now, in the outputter here, I'm actually outputting it with the definition of the outputter. So if you don't want to write if you want to have the code within your uSQL script, you can just put it into a string and then put it in here into the prologue. And then you just invoke it in the expression. So here you invoke it as orders outputter file finish because there is no wrapping class around it, no package, so to speak. Up here with the extractor, let's go back up here. The extractor is basically Python extractor.orders extractor because we have it inside that file that is a Python module. So if I run this, let me run it here just so you actually see something run. Although I will show you a job graph that was running a little bit earlier today. Because for some reason, actually, my tool, I'm not sure, Visual Studio seems to be fairly slow today in picking up the job graphs. So here you see now, I basically have that order table. And here you see now the Python code that has been run. So I have one vertex that did the extraction here. And then I basically split it, and there's like an outputter and a reducer. So if I double-click in here to see the actual kind of UI here, you will notice that there is the iReducer interface and the iExtractor interface. Now, right now, there's not enough tooling support yet to show you that this is Python. That is something that will be added once we go into like actual release.
Our existing Python support does show you that, but this new one hasn't quite integrated yet.
The new one has not been able to like get there yet. So this gives you kind of like a nice way of seeing what is happening here. And you basically have a very natural way of running Python. Now, if you go back and kind of look at what Python actually does today, we do have Python SDKs and the CLI for like all the management aspect of Azure Data Lake Analytics. And we do have this extension library with the Python extension that we have shipped for about 1.5 years. That only, however, runs in a reducer context, and it needs to load all the Python runtime when it creates the vertex, so it's fairly slow. We just recently increased the memory size to about 5 gigabytes, so you should not be running out of memory as quickly as you did before. But tomorrow, with that preview that I just shown, you can now do it natively.
And the feedback, I mean, for people with using the old Python was, it's a little cumbersome to write reducers all. It's weird to think of the problem that way.
Yes.
When all you want to do, for example, is do a one row in, one row out processing.
Yes.
The new model is much more convenient.
Yes, it's basically, it fits kind of the general notion of what you do inside it. So as I mentioned, public preview will be in summer. We will have all the UDOs available by then. We're still working on 1 or 2. We will be no longer restrained by the 500 megabyte per vertex limit. It will be 5 gigabytes approximately, and we'll have a feature also second half of this year where you can annotate on the UDO how much memory you think that the UDO needs, and then it can basically like request even bigger vertices. And there will be tooling support in VS Code and Visual Studio, etc. I'm skipping over this. These are just some examples of like writing an extractor or a native Python outputter. So this is just like showing you what we saw earlier. Yes?
Does it automatically manage the vertex memory, or does the end user manage
The vertex memory is normally managed by the runtime. So you get like a container has currently 6 gigabytes. If you request, you will have the option at some point to request bigger or smaller vertices, and at that point in time, you just give us a number, and we will get the next bigger or smaller container. And if they're bigger, I think you get charged more. Yeah.
Is that going to be like a subscription level, or is it going to be per job?
That's actually per operator.
Yeah.
So if you can annotate each of your UDOs, you can say, I need that much. And we are also giving you at the job level to override that. So for example, let's say you have a JSON extractor, and you know that, yeah, it uses the DOM, so I'm a little bit lazy. I don't want to write reader code. My normal sizes are such that I maybe need 2 megabytes for the JSON extractor, but on this job, I know I have a JSON document that is much bigger, so I can request 20 gigabytes of RAM. And I can like handle that way. Now, in terms of what happens when we deploy the vertex, so obviously we saw earlier we have this compilation. We deploy resources, scripts, etc. And then this is kind of the package that gets deployed onto the vertex. So you will notice there's a lot of like white stuff, which is basically the stuff that gets deployed for every USQL job. But if you know there's Python, we will get also, as part of the image, a Python library, so there is no special startup time needed for that. And then only the blue stuff that you deploy will get added on to the vertex. Now, we can do the same with Java. So let's take a look at Java. Now, Java is a little bit less far along, so I only have it running on my local machine right now. But it's very similar. What you do is...
Same pattern.
Same pattern, yeah. It's a little bit closer to our .NET pattern in the sense that I have to create an assembly.
Instead of the deploy resource.
Instead of deploy resource. But that's actually nice, because then when I reference the assembly, it really looks like, I don't care. Like as a user of the code, I don't care if it's Java or .NET, etc. Now I have to know it when I actually invoke it, unfortunately.
But all the data type interrupt just works.
The data interrupt works. It will know from the metadata this is Java, so it will basically make sure that then it knows that it needs Java runtimes, etc. And so what I do here is I have a simple TSV file. Let me actually open that quickly. So the TSV file contains some city names also written in the local script. So you have like some UTF-8 encoded data here. And I extract this, and now I'm applying a Java processor. Now this Java processor gets, again, I say processor.java or extractor.java, and then I have an expression for that creates me an instance of that extractor class or processor class in the Java context. And then in this case, I apply it twice, and then I do some join, and I write something out. So let's execute that locally here. So again, my laptop has a little bit age-induced comas here. Oops. That's the demo effect. Let's see if it works if I just rerun it again. Sometimes it does not. No. I'm not sure why that is. It actually did run a little bit earlier today. Let's see if I actually have a run open here somewhere. No, unfortunately not.
Hey, Michael, with about 8 minutes left, do you want, should I do the AU analysis too, or do you want to go through the Java stuff more?
I want to finish the other Java stuff.
Okay.
Because there's like
The
one
SERDI
more
stuff.
thing, the SERDI stuff.
Yeah, okay.
Yeah, because one more thing that we have is if you're operating on Java or on big data, there's a lot of extractors that exist in the open source world that are basically Hive SERDIs. So one of the things that the Java support will bring with you is not only that you can write your own Java extractors, etc., in the Java code, but you can also use Hive SERDIs directly. And so this is an example here. On the Hive SERDI side, for example, when you create your assembly, you will have to you can just refer to that JSON SERDI, for example. This is just a JSON SERDI that we took from OpenX. No changes whatsoever, whatever we got from the open source thing. We do have currently, we require you to like also co-deploy some of the Hadoop SERDIs that will eventually, I think, be built in as part of the experience. But right now you have to do it explicitly. And then you can just refer to that inside your assembly and then basically run this. And so in this case, I have a JSON document here that has some band data. Let me actually show you that. Where is it? Here. So this is just some array of JSON objects that contain beetles, etc. And it's actually kind of like the perverted array without the brackets around, which is not really JSON, but apparently Hive works with that anyway. And so I extract the band, all the property information, and I just output it into text file. Let's see if that works. And if not, I will be complaining to my, oh, I think I know why it's not running. When I set it up, it was halfway, the machine was rebooting itself, and I think that my Java runtime might not have gotten there. It's revival, so to speak, after the reboot. Yeah, trust me, it works on my local runtime when everything has. No, it actually runs here.
Oh.
So this is the local run experience that you probably know. So it actually now said, OK, it's done. So I can go and look at the SERDI output here. And as you can see, I schematized.
So basically it just worked.
It just worked. I just used my Java SERDI.
Fantastic. And we're going to ship with those in the future, right? They don't have to do all this create assembly and all this stuff, right?
Well, we will ship the framework part from the Hadoop side.
Yeah.
But obviously, you will still have to go and get the SERDI from that open source.
Oh, understood. Okay, we're not going to package that up.
We are not going to package those.
That makes sense.
Because obviously, you have your own favorite JSON SERDI
yeah.
or something. Okay, so let's go back to the presentation and go to the last part. So this is just the code that you've seen earlier, a little bit more detail. Here again, when I deploy the Java code, the Java runtime is part of the image, and the JVM assemblies will then be added depending on how you reference them. Just to show you, if I have a stage is basically that unit that have multiple vertices that operate on different partitions of the data. So when I have now one of these Python JVM environments, there's basically a type mapping happening between the C++ side and Python and Java. So there is no interrupt through C#. And then basically we provide these UDO APIs, and then you can write your Python or JVM Java code to operate against those UDO APIs and get back to it. For Python, we're also looking, I think, at data frames to make it easy to also operate with data frames. Although data frames, of course, have they load everything into memory, so they're a little bit less efficient than our UDO APIs. And then the data flows through. So let me get to the last part here before we overrun by 5 minutes. Splitting, we talked about outputting data and serving it. So one of the features that is a top ask on our website, which is now in preview, is the ability to have data that I can partition according to some column value into different files. So in this case, for example, you see I have IDs and amounts. And what I want to do is I want to lift the ID actually out of the row set into the table. There's actually a bug here on the slide in that the column ID actually is not part of the data anymore because now you lifted it up into the row set. So it's kind of the inverse. If you want to have a copy, you just have a second column that contains the data. So that was pretty hard to do, actually. It took us over 2 years to get where we are with this feature because it's the first time that NewSQL and our framework does not know about all the files at compile time.
Yeah.
So that means it now determines these files at runtime, and that actually was a lot of work. We finally got there. So today, when you write your code, you do what's on the left side, which is basically you write a lot of where clauses, and then you have one output statements per where clause select statement. And
there's a ton of generated code in Microsoft that does this, like thousands of these things.
Yes, and so I actually wrote a NewSQL script that generates this based on the data. And it's...
Everyone hates it, but that's how it works. Right?
Exactly. So today, and now with the output file set feature, you just basically do what you do on the input file set feature. You're just giving me a file set pattern, and now it will lift the things out of the rows. You can do date-time partitioning, etc. So let me show you.
And it just looks elegant. I think the right thing happens. It does exactly what you think it's going to do.
Let me show you an example here. Here is the script. So as you can see, I enable both my Parquet and my data partitioned output. And I extract the CSV file. Now this CSV file is 3.8 terabytes in size, just as a caveat.
Is that all?
Just, yeah.
Okay,
it's still small. And now what I do down here is I output this into a pattern that might be familiar to people that use Hive, so or Spark even. I use supplier equals key value as the partitioning. So I'm preparing my 3.8 terabytes of data to be used through Parquet by Spark or Hive or something.
So the Parquet outputter works just like any other of these
yes.
outputters. Fantastic.
So now the job, and I will point out one thing because we are in preview here. Basically, it did run for about 3 hours. If you look at the number of, it did read, it says here, almost 9 terabytes of data. I think there is a little bit miscalculation here. It had 47,000 vertices. If I zoom in here, you will notice that the extraction alone took 2,649 vertices because it's about 2.6 terabytes of data, or 3.02 terabytes of data. So it basically figured out that it can read that much data with that many vertices. Now, I did only run it with 100, so it wasn't that fast. It was running 3 hours. If I would have given it 2,650 AUs, I could have been done in 7 minutes. But my company is cheap. It doesn't give me that much money. And then down here, you see this very complicated job graph here part. That's where we calculate what are the partitions that we have to create. And then down here, we basically join the partitions back in and create in 3,000, we have 33,000 vertices here. That's probably because of the realignment here. And we are getting the Parquet file out. Now, this is not just one Parquet file. Let me show you what it actually creates. And of course, this has gone away again. Let me go up here, one up. Where do I go up here? Output, Parquet, big line items. And now you see here, I basically have...
Oh, because you had supplier equals as a folder.
Yes.
So you created the folders for the file.
Exactly.
Oh, that's quite nice.
And that's basically what Spark and Hive expects for partitioning information. And now the even better thing is I can go over and use Parquet to do some reading. So let's go and look at this thing here.
Wow.
So this is the Azure Databricks. Everybody in the big data team is legally obligated to give at least one Databricks demo at this conference. And so that's my part here. So what I do here is I basically created a notebook that is a SQL notebook. I created a temporary view over my line item view file that I had earlier, and my order view item. And now, assuming this still runs, let's see if that works. I should be able to execute this join here. Let's see, is it running or is it still giving me an error message? Let's just go through all of these. They're not taking that long. Now, you have to know that setting up a Spark cluster takes about, and getting it up and running takes about 10 minutes as well. So it's not a very interactive experience unless you really want to have it run all the time and spend a lot of money.
But this is one of the interactive stories we have, in addition to SQL DW Polybase.
Yes. So I'm creating these temporary views here. That already exists, and that's fine. Let's see if that one already exists as well. I think that was just now, so that's good. Takes 2 seconds, and now let's do the join here. So now the nice thing that I can do, of course, is besides like looking at this, I can do some nice visualization. So down here, for example, I count my supplier count, group by supplier key. And the Spark jobs run.
Wow. And that's a decent sized join, too.
Yeah, well, this one is a few gigabytes joined with a few megabytes, so it's not that big.
It's not the terabytes that we're talking about.
It's not the terabyte thing. I think this, I need to make this smaller here, unfortunately. So the nice thing about down here is, if you see what I've done, is I can also like very easily do some like nice visualization. So in this case, I was basically counting the number of suppliers for each supplier key. So you kind of see they are like going between 1,600 and this. If I want to see that slightly different, I, for example, could go and change this into a histogram to kind of see the distribution. Might be a little bit more interesting. So you kind of like have a very easy way of like doing some visualization here. And let me just show you the last one. I also did the same thing for that gigabyte, terabyte thing. So I created a temporary view. Now, creating a temporary view takes 8 minutes. Why would creating a view take 8 minutes? Any ideas? It's not really a view. It actually copies the data into the Spark cluster, into the in-memory kind of environment. So it's actually creating a temporary table in that sense, not a temporary view.
It's not just a lightweight metadata operation.
Yes,
Got
exactly.
it.
And then I do the same group by down here, and you can see that job ran about another 6.5 minutes to do simply the group by here. But it was running inside Spark based on the data that I cooked with USQL in ADLA.
Wow.
Okay, so now it's your turn
Can
again.
you switch me over? If you
Yes.
can give me exactly 1 minute, trust me, this demo sells itself. There's a job. Am I projecting? My power.
You're on A, but you're still PowerPoint.
Let's duplicate it here. So Michael showed you something about this a job graph, and he showed you this tab here. This is actually quite new, the AU analysis tab. Okay, let me minimize this here. And let me move this window up so everyone can sort of, see it. In a nice way. Okay, got the full screen now. The black line is actual. The job I ran, I asked for so many AUs. In fact, I asked for 50 AUs allocated right here, right? Took 7 hours. The black line is how...
It took
that's the cost. It took 8 minutes. But this is the cost, right? This is the number of active AUs. Notice there was a dip down here, and then it rose back up. That's great. So people really struggled. Where do you put the AU slider? How many do you ask for? What's cheapest? What's fast? What's the best bang for your buck? Well, we analyzed how these things work. There's a sort of like a series of curves to look at. But the long and short, what I want to show you is we pre-analyze these. So now when you look at the AU analysis, we'll tell you, for example, what's your best bang for the buck is balanced, the blue line. Right? And now you see, if you had asked for twice as many AUs, it would have taken much less time. 4.5 minutes, it would have cost you only a little bit more, 8 AU hours.
Basically, it would have cost you about a little bit more than 10% more, but it would have been almost twice as fast.
That's fantastic. Now, what if I really want to go fast? Whatever, and there's a definition in my PowerPoint what fast means. I can pay more, and it's going to cost, now it's 14.5 AU hours, but it's going to take 4.5 minutes. Efficiency is pretty low. And then what if you just want to play and just want to see, without running the job again, you can pick custom. And this is always the fun part. There's a slider. And you can actually learn a lot about performance of a job simply by dragging the slider. So watch. This is going to start at 1. Okay? So the black line is actual. The purple line is the custom. See how it happens as I approach the actual? It almost perfectly collided, meaning our heuristics are pretty good for this. And then, here's what and then balance, I go past balanced, and you can actually see now, if you pay attention to the number, the point of diminishing returns after balanced. Like I'm paying more and more and more money, but the runtime stays about 4.3 minutes. So you've passed the point where there's no point paying more. Yeah. Right? And you can interactively analyze it with the slider. And this is a really powerful thing, and you can learn a lot about your ROI for every job, right? And just so you know, we're planning on doing this not just for a single job, but we're going to auto-analyze for pipelines of jobs, right? So you can say, what's the sweet spot for the pipeline, not just for Ninja One. Anyway, that was my demo. Thank you. I think we're done then. Thank you for your patience. Appreciate it.